Hello everybody, I'm Amirmasoud Molaei. I'm a research researcher number 2 in the MORE projects.
Is that on?
Now, yes. Okay. I'm a research researcher number 2 in the MORE projects. I joined the MORE project in March 2021 and I work at Karlsruhe Institute of Technology under supervision of Professor Markus Geimer for 6 months, and after that I moved to Finland to work in Novatron company with Antti. And now I'm currently working in Liebherr company in Austria. For today I prepared a brief presentation. The topic is work performance evaluation of mobile machines. There are several research questions that we would like to answer. Why does the productivity matter so much? Who can get benefit from the productivity? What is the productivity? There is an important sentence: if you cannot measure something, you cannot improve it. This is so necessary for the improvement of the technology in that field. And firstly, we should try to define the productivity. What is the definition of the productivity for a machine in a task? Quantity or quality, which one is important? For example, one time a manager in a construction site only cares about the idling time of the machine, or maybe sometimes about the accuracy of the operation, as Antti talks about that. And what kind of condition, what operating condition can affect the productivity, the sewing angle, digging depth, the weather condition, skill of the human operator, all of these parameters can affect the productivity of the machine. By which sensor we can calculate the productivity? Vision sensor, such as LiDAR, or maybe the motion sensor using inertial measurement units or GNSS. And who can get a benefit from the productivity? A manager or a contractor, or maybe the operator inside the machine. This is very simple idea structure that we develop in the projects. In this project, we mostly focus on the excavator in 3 main tasks: loading operation, trenching, and grading operation. In the loading operation, the quantity of the material plays the main role. The manager only talks about how much material moves per day. Actually, the definition of the productivity is the volume or weight of the material per ton. But for the trenching and grading, this definition does not work anymore. And when the managers talks about the trenching operation, they say the linear length of the trench per time, or for the grading is the graded area per time. And in this operation, the accuracy or quality of the task is important. So, because of that, we develop a method for the automatic task recognition. Firstly, we want to find out what is the current task of the machine. We go to this box. This method consists of several parts. Firstly is the motion sensor. We installed 4 IMUs, inertial measurement unit, on different moving parts of the machine to get the motion information from the different movement of the machine, the variables such as global angular velocities, local angular velocities, and joint angles from the bucket, arm, boom, and also the cabin of the machine. The next step is the data collection. We did a lot of experiments to collect enough data in different weather conditions during 1.5 years by using our machine in Novatron, Komatsu excavator. The swing angle in the operation was between the 60 to 120 degrees. That we use different type of material, sand, gravel, and also 2 operators did the operation. Me as an inexperienced operator, and one of our colleagues in Novatron as a very, very experienced operator. The next step is the data processing. We decided to identify the task of the machine based on the time window. We implement different size for the time window, 10 to 20 seconds, and the overlapping between the two consecutive time window can be between 0 to 75%. For the data annotation or ground truths, we use another camera installed on the machine, and actually the most frequent label in each window is chosen as a label of that window, and we have 4 different labels for the task: loading, trenching, grading, and also maybe the machine is idling. And also we use the 10-time domain statistical feature for the feature extraction from the data. And also we use 3 different feature selection methods for this classification problem. The final step is the training and evaluation. You can see the result that we present in our papers. We implement 4 supervised learning algorithms for this classification problem, and we were able to achieve the high accuracy of 99% for this classification problem, this task recognition. Now we know what is the current task of the machine. Just we can talk about the productivity. For the loading operation, we try to implement this instruction for the loading operation. We try to calculate the normalized index to show the performance of the machine. How we can calculate this index, production performance ratio? To calculation of this index, we need to know the actual productivity and theoretical productivity. Actual productivity can be calculated using the actual cycle time and also the quantity of the material each cycle. But because already there are some research that there are some methods that already developed for the dynamic bucket payload estimation or bucket volume estimation, we didn't do any research for that. But we developed very accurate model for the actual cycle time estimation by using a subtask recognition method. But what is the subtask recognition? It is very, very similar to the task recognition, but now we are only talks about some small tasks that maybe takes only 1 or 2 seconds. The motion sensor and data collection steps is completely similar to the task recognition, but for the data processing, we should reduce the time window. It can be 0.5, 1, 2, 3 seconds. And now the labels are different. The scoping, swinging, loaded, dumping, swinging, empty, and idling are the 5 subtasks in the loading operation that excavator can do. And the feature extraction and feature selection step is the same. And the final step is training and evaluation. Now you can see the result of our method. We can achieve the accuracy of 95% for the subtask recognition. We implemented 4 different classifiers for that. Now we can recognize automatically what is the current subtask of the excavator in the loading operation. How can we calculate the actual cycle time of the machine? You can see the excavator in a duty cycle in the loading operation. Actually, the cycle time is the time between 2 scoping activities, if there is a one swinging loaded, swinging empty, and dumping between them. Now you can see the result of our method. We can achieve the accuracy of 97% for that cycle time estimation. The error between the ground truth and our estimation is less than the 1.5 second for the cycle time of the excavator in the loading operation. But this part, For the theoretical productivity estimation, we need to know what is the current condition in the work site. For this operation, what is the swing angle, what is the digging depth, or maybe what is the material that excavator are working on it, or maybe the size of the excavator. We developed two methods for the swing angle and digging depth estimation. The previous method we presented in the previous events, but now we are trying to estimate the swing angle using the subtask identification. Actually, the swing angle is the absolute deviation of the between the scoping and dumping position. How can we calculate the scoping and dumping position by using the subtask identification? Actually, scoping position is the average of cabin encoder measurement in the scoping subtask, and for the dumping is the same. By using the absolute deviation of the scoping and dumping position, we can calculate the swing angle. As you can see, the result here is the you can see the result for the experienced operator. The experienced operator can easily handle the swing movement of the machine, but for me, it is obvious that I'm not expert in handling the swing movement of the machine. But the method can effectively recognize the scoping and dumping position of the excavator. And also for the digging depth estimation is the same. Actually, the digging depth is the minimum of the bucket tip position in the scoping subtask. By using the inside IMU on the machine and also the kinematics of the machine, we can estimate the bucket tip position all the time, and after that, by using that, we can estimate the digging depth of the machine. And you can see the result, and the method can estimate the digging depth in each cycle. Okay, here we are trying to estimate what is the theoretical productivity or theoretical cycle time of the machine. We did some research, and there are some limited methods for the theoretical productivity of the machine from some big companies such as Komatsu and Caterpillar. And also, we cannot use the model from the Caterpillar because it's a descriptive model and it needs the human decision. But we implement the Komatsu and BML method in the automatic manner. The BML guideline is a German handbook that try to provide some models for the theoretical productivity of this kind of machine. And our results show the Komatsu model is more optimistic, but the BML guideline is more realistic, and we decided to use the BML guideline. We need 4 inputs for this model: swing angle that we estimated, digging depth we estimated, and also the bucket capacity we can suppose we know it. But for the type of the material, for this research we suppose we already know it, but maybe in the future we can run some algorithm for the automatic material classification, because the type of the material plays an important role in the productivity of the machine. By using this mathematical formula, we can estimate the cycle time of the machine. Now, by using the actual cycle time and the theoretical cycle time, we can calculate this index, PPR, or production performance ratio. As you can see here, we categorize this index in 3 classes. The area over 0.8, it means the satisfactory performance, and the area between the 0.6 and 0.8, it means the average performance. And you can see performance of my operation. Mostly it is in the yellow area, but our colleague in Novatron, as an experienced operator, it is in the green area, and it shows better performance in the same condition. that was our idea for the productivity estimation of the excavator in the loading operation. But definitely this definition doesn't work anymore for the other tasks. For the trenching operation, we tried to implement a similar structure. There are some problems, but I think finally we can implement this algorithm. For the actual productivity, we want to calculate the length of the trench per time. But who provides for us the model from the desired model, or how can we see the surrounding of the excavator to check what is the productivity, or how can we compare the desired model with the actual terrain in the work site. To see what is the current condition of the work site, we need a 3D vision sensor. In Autonom, we implement the algorithm by using the LiDAR sensor on top of the machine and IMUs and GNSS to develop a grid-based height map, top and deep map, to model the working area of the excavator in the surrounding area. And for this algorithm, I don't want to talk in detail about this algorithm, but we have some challenges for the transformation of the data from sensor frame to the machine frame, and after that machine frame to the global frame. And also, in this algorithm, we only want to cover the area that excavator can touch, the bucket of excavator can touch. And the far from the excavator is not important for us. Because of that, we try to crop the area around the excavator, only can see the working area. And also because the LiDAR sensor is on top of the machine, always we have some extra points from the movement of the manipulator of the machine. We estimate the all position of the manipulator of the machine, and we try to remove the points from the point clouds. This step provides the actual happening in the what is happening in the work site. But about the desired model, Antti talks a lot about the BIM or building information modeling. This model can give us a lot of information about the target of the target model in the work site. In Overtron, we installed the Excite Produce system in the cabin of the machine. By using this hardware, always the operator can compare the bucket tip position to the target model and do the operation. How much time? Okay. I will handle it. Okay. Now we can calculate the productivity estimation. What was the definition? Linear length of the trench per time. We consider a region of interest. Actually, it is a narrow stripes of the trench. And always we can compare the elevation of this stripe to the desired model. And when the error, the difference between the target and the actual one, is reduced to the value less than the required accuracy, it means the positive productivity. But sometimes some materials fall to the trench, or the operator is not good at the operation and go too deep, it means the negative productivity. And as you can see, the result of the method that here is the aggregate productivity. For the grading operation, we try to implement a similar idea, but the definition of the productivity is different, and Now the region of interest is a square, and we always compare the elevation of this square with the what is in the work site. And if the error becomes less than the threshold or less than the required accuracy, it means the positive productivity, and if it goes higher than the required accuracy, it means the negative productivity. That is our last slide. In this project, we try to propose a method for the productivity estimation of excavator in 3 most important tasks: loading operation, trenching, and grading operation. We had some problems with the theoretical model for the theoretical productivity estimation of excavator in the grading and trenching operation. And until now, we were not able to calculate the production performance ratio. And we are thinking about implementation of some similar methods that we did for the loading operation for the wheel loader. Hopefully, we can implement that. Thank you so much. That was my presentation. I'm happy to answer questions.
Any questions? We went over our coffee time. Okay.
You said in the subtask recognition you had an accuracy of 95%. So is this good? What would you say? Is this good enough?
Yes, I think it is good enough because our main target is the cycle time estimation. And in the cycle time estimation, we were able to achieve the accuracy of 97%. And the error, most of the time, it is less than 1 second. And in the work site, the error for the cycle time less than 1 second, it is enough.
Then you also had this theoretical estimation of the cycle time.
Ye- Okay, I think about this solution, but because it is a very complicated process, it needs a lot of data, it needs a lot of experiment. Imagine different size of the excavator, different type of material, and maybe 5 or 6 another parameters we should choose. And in this project, we were not able to collect this amount of data. For example, we have only 1 machine, and only proposing a model that works only for machine doesn't make sense. Because of that, I searched only there are some limited methods, some maybe 2 or 3 methods that provides from the big companies, from the big experiments, Komatsu, Caterpillar, and some handbooks. And it is not easy to provide a model that everybody can use it.